Hey, hello everybody. I'm Dai Ying from Nanyang Technological University, Singapore. I want to first thank the organizer who provides such a nice choice of location. So Simalo is very beautiful, so I'm looking forward to the next choice of location. Yeah. So this work is going to be, I'm talking about expressiveness and structure preservation when we learn Hamiltonian system, when we learn part Hamiltonian system. And this is a joint work with my supervisor, Juan Pablo Ortega. So we want to first start with considering a continuous time state space system of this form. Z is your state, F is the state map, U is input, and Y is output. H is the readout. So Z is your state, and you have input-output system defined like that. So physical systems, they are formulated in terms of such ordinary delayed or partial different equation, for example, Hamiltonian systems. And then when people do machine learning on that, typically they use neural networks because of the universality property of neural networks. But the problem is neural networks, they don't preserve the physical structures. So what we want to do is structure preserving, because preservation of structures will lead to both qualitatively and quantitatively better numerical result. So for example, you can look at the success of symplectic integrators, because without the symplectic structure, when you integrate the system, you get a long time, in a long time the error blows up. But if you preserve the structure, you can get a reasonably better numerical result. So nowadays, typically what people do for physics-informed machine learning is they typically just apply penalization, right? If we don't respect the Hamiltonian equation, I just penalize it when it doesn't respect it. So today you're going to see what we are doing here is a little bit different, because we want to do a little bit different approach, because we want to start from the differential equations themselves. So by the differential equation, I mean part Hamiltonian systems. It's a combination between a Hamiltonian system and the network point of view, because you have input and output. So the underlying structure of this is called the Dirac structure. So it's a generalized notion of a symplectic structure and Poisson structure. So in the input-output form, it looks like this, where J is a skew symmetric interaction matrix, R is a dissipation matrix, positive definite, and then the little g is input-output connection structure. So this is the generalized notion of such a system. So for example, you can look at a very simple case where your J is canonical symplectic. You don't have dissipation, so it's in no R. And your G is basically 0, 1, so it looks like here. So it looks like in one dimension, it looks like a Hamiltonian system with input, because your U affect your momentum. So for motivation, you can define your Y, which is the output, as Q dot, because in this case, your U times Y, which is your input times Q dot, which gives you the time derivative of the Hamiltonian, which is power. Right? Think about, for example, voltage times current gives you a power as a circuit. So by a different approach today, I mean, we want to start with a very simple case, and we see what we can get out of it. So by simple, I mean we are focused on linear part Hamiltonian system today. So the J that you see just now is a canonical symplectic matrix, and you don't have dissipation. Okay, and your G. The G just now become a constant matrix B, so vector. So B is a vector, Q is a matrix, and the system looks like that. So I would call it the part Hamiltonian system in a normal form, because it's completely determined by Q and B, where Q is a matrix and Q is a symmetric matrix, B is a vector. So for example, I can give you such an example. So it's a circuit. It's non-dissipative because I'm not adding dissipation here. And the Hamiltonian, you can write it down like that. And you can write it down in the part Hamiltonian system that I gave you just now, like a system equation like that. So U here is voltage, and Y here is the current that flows through the power plant, right? So here is a parallel connection of inductors and capacitors, for example. So as a motivation, we need to introduce two tools in order to study such systems. The first tool that I'm going to introduce is called system morphism. So a system morphism is a function that is between two state space systems, and then it has to satisfy two conditions. The first condition is system equivalence, which means the state map should be equivalent with respect to this F. The second condition is called readout invariance, which means So the readout has to be invariant when you read out from both systems. So if my function satisfies these two conditions, I call it a system morphism. And then if this is invertible and its inverse is also a system morphism, I call it a system isomorphism. So in general, input-output systems, they are not uniquely identified because when I give you a state space realization, they could be isomorphic, which means you cannot distinguish them in terms of input and output only. So in this case, I will show you actually don't need to distinguish them because there's no way, because you only observe the input and output. So it's the first tool. The second tool is very classic. It's from classical symplectic geometry. It's called Williamson's form. For example, if you have a M, which is a positive symmetric definite matrix, then there exists a symplectic matrix such that it diagonalizes your matrix M in this sense, where you have a diagonal matrix where it's D, 0, 0, and D, and all the diagonal matrices there are positive. And moreover, this D, the order of the D does not depend on the choice of S. And also, if you have two different S, such an S is not unique, but they are deferred by a unitary matrix. So all these are very important later. So now I give you the tools. Now I tell you how I do my machine learning, right? So given a power Hamiltonian system like Q and B, so what I'm gonna do, how I'm gonna use Williamson's normal form is I take the decomposition of Q, which gives me D and S, where D is diagonal and S is symplectic, and then I multiply this S together with B. It's a vector, so I call it V. So the diagonal matrix is D. I just treat it as a vector, so it's a little d here. So from Q and B, I can give a D and V. So on the other hand, start with the D and V, I can make it diagonal, for example, and then I take any symplectic matrix, which is S, right? And I can form a positive definite symmetric matrix Q by just conjugate this diagonal D by this S transpose and S. So what I'm telling you here is, starting from left-hand side Q and B, I can give you a D and V, and starting from D and V, I can give you a Q and B in that form, where S is basically any symplectic matrix. So now I'm gonna introduce my first definition. So I call such a system here controllable Hamiltonian representation. So it's just another continuous time state space system. You have input-output state, but now state is called S. And then it's this specific form. It's totally explicit. This G1 is a matrix which, if you know control theory, is basically a canonical form. All right. So how I get all this A? So the A's, they are variables. How I got it is as I match the characteristic polynomial and the polynomial in terms of A. So I just read the A from this matching. Okay. So I tell you what this G1 CTR is. The other one is G2 CTR, which is in the readout. It's a vector. So this is more complicated. This one, there half of the entries are zeros, and the other half of the C's, they are given by this expression here. And this expression here, you have Fk. Fk is defined with this diagonal thing, and then each of this entry is again a function of all these D's. So I'm just gonna define the set of D and V's by Rn, and by Q, a set of Q and B's by Phn, which is a set of power Hamiltonian system. So now I'm gonna tell you why I care about this reparameterization, right? Because given any D and V, I can give you a system like that, right? So why do I care about such a representation? Because I can prove a theorem. So the theorem says for any S, so give me any symplectic matrix, so there exists a map from any D and V to some power Hamiltonian system, so that they are linked by an explicit system morphism, which means, so recall what is the definition of system morphism. It means no matter what D and V gives you, the input-output dynamical systems are represented by this controllable Hamiltonian representation is also an input-output dynamical system of this power Hamiltonian system. So by this, I achieve what I mean by structure preservation, because no matter what D and V I give you, I form you the controllable Hamiltonian representation. The input-output dynamics of it is always a power Hamiltonian system. So that's very important, because this is truly what we mean by structure preserving, right? Because even if I estimate D and V with error, what I get in the end is always automatically power Hamiltonian by construction. So this is the first part, controllable. So if you know system theory, there is a dual notion of controllability. Okay, I forgot to mention what is controllable. So controllable means by varying my input, I can get any state. I can get my state to arbitrary state that I want. So that is controllability. So I talk about observability. Observability means by looking at the output, I can distinguish the input. Okay, so it's a dual notion. So just now I give you the importance of controllable Hamiltonian representation, and then there is an observable Hamiltonian representation. So what is that representation? It's basically all the matrix here is transpose. Okay, it's a dual. So everything here is a transpose. So the controllable Hamiltonian representation is just everything transpose of this representation here. So that's why I didn't type it out. But why do I care about observable Hamiltonian representation? Because I have another theorem that tells me no matter what Q and B, no matter what the polar Hamiltonian system you are giving me, there exists a linear morphism between the space of Q and B and that of observable Hamiltonian representation, which is parameterized by some D and V, right? So why is this important in machine learning? Because no matter what the underlying system is always parameterized by Q and B, right? But there always exists a D and V that gives me exactly the same, that captures the input-output dynamics. So this is somehow important in the machine learning context that is known as expressiveness, right? Because how powerful is your parameterization? Can you parameterize any dynamical system they are giving me? Actually, I prove it for you. Yeah. So now I can bring these two representations together because from the control theory, they are equally important and they have very strong correlation or relationship. So the significance of this representation, I can summarize it for you, is structure preserving. The controllable one is structure preserving. The observable one is has a full expressive power. And then these are linked by matrix transpose and they coincide for canonical polar Hamiltonian system. By canonical, I mean both controllable and observable. And what is worth note is that so the canonical systems, they are dense in all systems. So basically almost all systems, they are canonical. So which means basically for almost all systems, the controllable Hamiltonian representation is isomorphic to the observable one. And then computational complexity, when you estimate the system is reduced from O(n) squared to O(n), right? Because before you need to learn the Q, which is a matrix. Now you only need to know the D and V, which is a vector. So you reduce the complexity. And what is very important is actually the last line. So both representations exhibit symmetries. So there is some inherent symmetry here, which I'm going to tell you now in 2 slides. So now I'm just going to look at the subset of canonical polar Hamiltonian system, right? Remember, these are almost all, these are dense, right? So what is a canonical? I can characterize it as, you look at D and V. So what is a canonical Q and B? You just look at it as D and V. So if all the D's are different, which is known as a non-resonance condition in dynamical system stuff, and then if your V, because your V is 2n dimensional, if your V satisfies this Vi squared plus Vn plus I squared is strictly larger than 0, then I call it, I can show that it's corresponding to the canonical system. So from this characterization, you can see very clear that they are almost all, right? They are dense, okay? So I'm just gonna denote the Phn canonical as a canonical system and Rn canonical as a canonical subset of D and V. So they are both they are both dense. So this is the most important slide in my talk. So what do we want? Because I'm doing machine learning, right? So what we want is we want to characterize the Phn quotient, the cis. That cis means the equivalence relation of system isomorphism, right? I want, because when two systems they are isomorphic, they are not distinguishable. So I don't want to distinguish it. I look at the quotient space. I want to characterize the quotient space. So I can prove that it's actually the equivalent classes. They're actually the groupoid orbit space for some groupoid. So groupoid is just a generalized notion of group, right? It's a symmetry. So Gn here is a groupoid. So I can prove that they are isomorphic. So, but I cannot further characterize it, right? It's very hard to further characterize it, but I found this possible when I restrict to the canonical subset, right, which is dense. So as long as you project to the canonical subset, you can I mean, you can prove a lot of isomorphisms, but in the end, you can see the symmetry is given by the semi-direct product of the permutation group and a torus, basically. And then you can even characterize it explicitly as a subset of some Euclidean space. So this weird notation here basically means the n positive numbers which are strictly increasing order, right? Because I permute them, I quotient the permutation. So to summarize, I prove that the canonical, the set of canonical Porte Hamiltonian systems quotient out the system isomorphism as equivalence relation is isomorphic to this Euclidean subset. So what it means in machine learning is when you want to identify the input-output dynamical systems, you basically need to learn some parameters, right? So what are the parameters is here, right? It's a subset of Euclidean space which you can do gradient descent, right? Because in general, quotient space, you cannot do gradient descent. You don't know how the space look like, but now you know it's in Euclidean space. You can do whatever you want. Yeah. So let me see if I missed something here. Yeah, I think it's fine. But so I just emphasize that this is called uniquely identifiability because I can uniquely identify the Porte Hamiltonian systems by some parameters, and then I can do machine learning on that. So this thing, this Euclidean subset is my parameter, and what is my model, right? Because I have my parameter. So, but where is my model? My model is exactly the same as I tell you before, the controllable or the observable Hamiltonian representation, okay? So now you have the model, you have the parameter, you can do machine learning. So for example, I'm taking the circuit I just showed you in the very beginning. So the first two plots, so the left one is the input, and the right one is the output, right? You see, I only train it a little bit, like for 10, right? Like a little bit time, and then I test it. It's performing perfect, basically, because because we have very few degree of freedom here, so it's very easy to train. And then, because what I learned is the dynamical system itself, it should be independent of the input. So if I change the input, it should also work. So downstairs here, I didn't retrain it, I just changed another input and predict, and it also works very well. And I change other input, right? All these inputs, they are very standard in electrical engineering, for example. And you see, it can work very well, yeah, with just a little bit training part in the beginning. So another thing I want to talk about is, because I go to the quotient space, right? So I can learn it in the just D and way, but I in the end learn it in the quotient space. So what is the advantage of learning it in the quotient space? I just show you here. So the left one is learning without quotient, because so you don't quotient out the symmetry, and learning in the quotient space on the right. So just if you run the algorithm for the same number of iterations, you will find that the left one converges way slower than the right one, which means I plot it here. So if you see it, the error is logarithm of the validation error. The x-axis is the iterations. So this is log, it's linearly faster, so which means it's actually exponentially faster when you go to the quotient space, right? Because in the quotient space, you quotient out both the permutation symmetry and the rotation symmetry given by the torus. So this demonstrates when you make the machine learning problem well-defined, it goes very, very fast. So in conclusion, what we do today is we study linear Porte Hamiltonian system in normal form. So we didn't touch nonlinear. Nonlinear, the methodology doesn't work because you cannot compute stuff anymore. So you have to change. So we have to change another method. Yeah, but this is linear. But I hope it inspires some symmetry characterization. And we construct two representations, and we identify the symmetries of Porte Hamiltonian system as a Lie group or Lie group, right? And then we characterize the quotient space explicitly as a subspace Euclidean space. And in the end, we allow by construction, structure preserving, machine learning, and dynamic dimension. So this part didn't touch, but we also allow some dimension agnostic learning Porte Hamiltonian system. So these are my So this is a TSI paper. It's a new paper that we submitted already. Yeah, thank you. So happy to answer any questions here.
Okay, now, yes. Questions?
Sure.
No questions, but probably from me then. So
Uh-huh.
what you find, so what kind of tools are you thinking of applying when you would be moving to nonlinear case? Are there any
Yeah.
ideas about that?
So yeah, as you can see clear, so the entire construction is based on the linear thing. So you can do Williamson decomposition, but this Williamson decomposition, the analog doesn't exist for nonlinear case. So for nonlinear case, actually what we are doing now is another approach, which is we are trying to use a Gaussian process, the RKHS formalism to learn Hamiltonian system. So there is a different approach because we are learning where the input data in the other approach is Hamiltonian vector field, and what we are learning there is Hamiltonian, which assume lives in the RKHS, the reproducing kernel Hilbert space. But that's going to be a very different approach from here. Yeah.
Okay. More questions? Okay, let's thank the Ying then once again.